Welcome to The Explainer. Today we're going to tackle a question that we all think we know the answer to, but trust me, the reality is way more fascinating. I mean, you see these incredible machines slicing through the clouds pretty much every day, but how do they actually stay up there? We are going to deconstruct one of the most common myths in science, and then we're going to build the real story of how airplanes fly, piece by piece. Okay, so most of us, right, we learned this really simple story back in school about how wings work. And it's one of those things that's super intuitive, it's easy to get, it just feels right, it makes sense, and hey, it's been taught for generations. So let's revisit that explanation we're all so familiar with. All right, so let's talk about that story. It's often called the equal transit theory, or you might have heard it as the longer path theory. And it's this really elegant idea that tries to connect the shape of the wing directly to the force that lifts it. And honestly, on the surface, it makes a whole lot of sense. So the basic idea goes something like this. Picture a single little parcel of air hitting the front edge of a wing. It splits in two. One part goes along the flat bottom, and the other has to travel over the curved top. Now, the theory says these two parts are somehow destined to meet up again at the exact same moment at the back of the wing. And this is where the logic seems so perfect, right? If the top path is longer, and the travel time has to be the same for both, then just basic math tells you the speed on top has to be higher. The air over the top has to literally race to catch up with the air that's taking the shortcut underneath. It all just clicks, doesn't it? And this all ties up neatly with the famous Bernoulli's principle. Faster moving air has lower pressure. So you've got fast, low-pressure air on top, and you've got slow, high-pressure air on the bottom. The high pressure below pushes up more than the low pressure above pushes down, and voila, you get lift. It's a beautiful, self-contained story. There's just one tiny problem. It's wrong, totally wrong. And this is where the whole thing just falls apart. See, the entire explanation hangs on one single assumption, that those air parcels must meet up at the back at the same time. Well, as it turns out, there is absolutely no physical reason why they have to. In fact, wind tunnel experiments using smoke puffs prove it's totally false. The air going over the top actually gets to the back of the wing much, much sooner than the air on the bottom. So get this, the entire foundation of that story we all learned, it's just not right. It gets a few things right, like there is lower pressure on top, but the reason why is completely wrong. So, okay, let's just build a new, much more accurate understanding from the ground up. The truth is, lift isn't some single magical thing. It's actually a beautiful combination of several different factors all working together. Yeah, it's a little more complex, but it's also a whole lot more interesting. Let's break down the three key ingredients. Okay, so we're going to look at our three main players in this story. A simple upward push, a real pressure difference that's created for a very different reason, and even the surprising stickiness of air. All three of them have to work together to keep a massive airplane soaring through the sky. And here's something that might just blow your mind. That famous curved shape of a wing, it isn't even necessary for lift. Think about it. A simple flat wing, like on a paper airplane, or even just your hand sticking out of a car window. It creates lift just by being tilted into the wind. That angle is called the angle of attack, and it is fundamental to our very first ingredient. And that brings us right to our first key ingredient, good old-fashioned physics. The wing, when it's tilted at an angle, pushes a huge amount of air downwards. That's the action. And so in response, the air pushes the wing upwards. That is the equal and opposite reaction. This downward deflection of air is a huge source of lift. At the end of the day, a wing is basically just a really, really efficient air deflector. Okay, so there is a pressure difference. We're not throwing that out completely. But it's not because of the longer path thing. As the wing plows through the air, it basically creates a traffic jam of air molecules right at the front, building up this cushion of high pressure. And that high pressure cushion, in turn, creates a zone of lower pressure, almost like a vacuum or a shadow, just above and behind it. And see, this totally flips the old story on its head. That low-pressure shadow effectively sucks the air over the wing's surface, and that forces it to speed up as it rushes into that region. So the speed is a result of the pressure difference, not the cause of it, which is the exact opposite of what the old theory claimed. All right, our last ingredient is a little weird, but stick with me, because it's super important for making a wing work well. Fluids, and that includes the air we're flying through. They have this property that makes them want to kind of adhere to a surface they're flowing over. Think about how honey wants to stick to a spoon and follow its curve.
So this Kawanda effect is what makes sure the air doesn't just, fly off the top of the wing into space. Instead, it actually hugs the top surface, bending the entire stream of air downwards much more efficiently. And this just enhances that downwash we talked about with Newton's law, making the whole process of deflecting air a lot cleaner and way more powerful.
Okay, so now we've got the real story of lift. But lift doesn't operate in a vacuum. To really truly understand flight, we need to see how it fits into this constant tug-of-war that's happening in the sky. It's just one of 4 fundamental forces that a pilot has to constantly manage. Think about it like this. For a plane to just cruise along nice and steady at a constant speed, all 4 of these forces have to be in perfect balance. The upward force of lift has to exactly equal the downward pull of weight, and the forward push of thrust from the engines has to exactly cancel out the backward force of air resistance, or drag. So literally every single thing a pilot does, taking off and climbing, making a gentle turn, descending for a landing, it's all about intentionally messing with that balance. It is a continuous 4-way dance in the sky. All right, let's take a breath and zoom out for a second. We've busted a really common myth, and we've replaced it with a much richer and, frankly, more complete picture. So let's just summarize the true, multifaceted nature of flight. So here are the 5 big things you should really walk away with. It's not one simple trick, but it's this beautiful interplay of powerful physical principles, from Newton's laws all the way to fluid dynamics. It all comes together to make flight possible. And when you start thinking about this more complex reality, it just opens up all these cool new questions. Now that we truly get the forces at play, the downwash, the pressure gradients, the surface effects, how can we design even a more efficient, quieter, and more innovative aircraft for the future? The sky, it turns out, is still full of possibilities. Thanks so much for joining me on this one.